Hello, I am Pratyush Maini, and I am happy to present our work on Dataset Inference for ownership resolution in machine learning. This is joint work with my collaborators Mohammad and Nicolas at the University of Toronto and Vector. Resolving ownership in machine learning is becoming increasingly important because developing high-performing ML models is becoming expensive due to various factors such as the high computational cost involved in training these models, the large amount of time and money required to gather and label a private dataset that helps achieve high performance, and algorithmic and architecture novelty that contribute towards the intellectual value of your model. As ML models become valuable commodities, adversaries eye towards stealing them by copying a victim model's predictions at a significantly lower cost at their end. One such popular way of stealing ML models is called model extraction. This may happen when you, as a victim, aim to deploy your ML model as an API over the web, such as on the left in the image on the slide. This is a distillation-based attack where the adversary typically queries the victim on multiple data points from a freely available public dataset and leverages its predictions to train an alternate ML model at a much lower cost. In fact, recent work has shown that model extraction can be successful even in a data-free setting relying only on synthetic data generation. Alternately, model stealing attacks may be staged in scenarios where the adversary has varying degrees of access to the victim's knowledge. We consider 3 scenarios, and in each of the cases, the goal of the adversary is to train an alternate ML model that provides high task accuracy while distancing its predictions from the victim in order to stay conspicuous. First, the adversary may gain complete access to your private training data. This may happen due to insider access or because you release the dataset for academic purposes alone and not its commercialization. Second is query access, which we discussed in the previous slide and is often called model extraction. Third, the adversary may have access to your entire model, such as if OpenAI were to release GPT-3 for academic purposes without permitting its commercialization. The various strategies that the adversary may employ to steal the victim's knowledge given this access or the threat models are further detailed in the paper. Given an unrestricted data access, query access, or model access, it is impossible to prevent model stealing. As a result, recent works have focused at detecting model stealing attacks post-hoc, that is, after the attack is completed, via methods such as watermarking and fingerprinting. The key idea behind watermarking is to embed a signature such as a logo with a particular label such as label 9 in the image below while training the model. The hope is that such an attribute also transfers to all student copies. However, learning such signatures requires retraining the victim, which can be expensive in itself and also has been shown to have a task trade-off with task accuracy, thus diminishing the original model's utility. Finally, it has been found that an adaptive adversary may be able to remove the signatures during their training. This starts an arms race where the victims modify the defenses to circumvent a recently proposed attack, while attackers utilize this knowledge of the defense to remove the watermarks. Instead, we propose Dataset Inference, which is a fundamentally different way to detect model stealing and does not require retraining or have a trade-off with task accuracy. Dataset Inference builds on the hypothesis that there exists a key distinction in the behavior of any point in the training versus the test set of an ML model. We call this the prediction certainty. The underlying idea is that during training of an ML model, the optimization step pushes boundaries of incorrect class labels further away from points in the training set. However, the same opportunity for modifying model weights is not provided to points in the test set. As a result, point x, a pushes class boundaries b, c, and d away from it when in the test set, training set on the left, but no such direct influence occurs on the right. As an expectation, over multiple samples drawn from these two distributions, we will observe a difference in the prediction certainty or the prediction margin. We validate our claims on linear models with theoretical analysis on a simple binary classification task with labels -1 and 1. Any input x is the concatenation of k-dimensional component x1, which linearly separates the data based on the class label, and a d-dimensional component x2, which is simply Gaussian noise with no correlation. We show in Theorem 1 how there exists a difference in the expected prediction margin for points sampled from the training set versus the test set. The simple intuition is that the optimization step updates the weight in such a way that after an epoch of training, W2 is effectively the mean of Gaussian noise with sign of the corresponding label. Eventually, when we calculate the effective margin, which is f of x for a linear model, this ends up having a higher expectation for data points sampled from these xi's that find themselves in the model weights. In fact, a similar intuition is also central to a privacy attack in machine learning called membership inference. The goal here is to infer whether a given data point was present in the model's training set or not. Such attacks often rely on a classifier that detects the difference in the behavior of a model to points in the training versus the test set. However, in our work, we prove in the case of linear models that the success of membership inference goes down to 0.5 as the size of the training set increases. In fact, our theorem complements practical observation by past researchers where they have required to overfit models on small datasets to allow membership inference to succeed. While MI is a privacy attack, on the flip side, dataset inference is a defense that victims may employ to detect model stealing. The key difference is that victim has access to their complete training data and can aggregate and amplify membership signals for multiple data points in and outside the model's training set, which allows them to perform hypothesis testing to distinguish the two distributions rather than having to set arbitrary thresholds to dispute membership. Therefore, as long as the adversary does just slightly better than random guessing, they will succeed at dataset inference, whereas this would not be satisfactory for MI to succeed. This asymmetry gives a strong advantage to the defender and flips the adversarial game on its head. While the success of membership inference goes down to 0.5 with increase in data, in the same setting, we show that dataset inference is independent of the size of the dataset, and as the dimensionality of the data increases, the success of probability of dataset inference goes to 1. While the theoretical results for linear models show promising signs for dataset inference, how do we scale to deep networks, where calculating the prediction certainty or margin of a point is typically non-trivial? We propose blind walk, which is a black box method to estimate this quantity. We sample a random noise direction and then keep taking small steps in the same direction till we reach an alternate class. We note this distance and aggregate a feature vector over multiple initial directions to create a more informative feature embedding. We further use different types of initializations like uniform, Laplace, and Gaussian noise to increase the amount of information that we can capture about a point's local landscape and augment this into a combined feature embedding. Once we have our feature embedding, we train a confidence regressor to output high confidence scores like 1 for embeddings of points seen during training by our victim model FV and 0 otherwise. Now, we're ready to dispute the ownership of any ML model once we have a regressor trained on these features from the victim model. Given a suspect ML model, we will follow a 4-step process to dispute its ownership. First, we sample inputs from the training and the test set of our victim model. Then, we generate feature embeddings that represent the prediction certainty with respect to the suspect ML model. Third, we pass these embeddings to an auxiliary regressor that we previously trained using features of our victim model. If the adversary stole our knowledge, we would expect a similar response to transfer to its predictions. And finally, we aggregate these confidence scores or distributions and perform a one-sided t-test with the null hypothesis that the mean confidence score for points in the test set is more than that for those in the training set. If H0 is rejected under the set p-value, we claim ownership of the suspect ML model. Dataset inference shows promising results across a variety of ML benchmarks such as CIFAR100, SVHN, CIFAR100 and ImageNet. We find that using our blind walk method, we can resolve model ownership in less than 60 private samples of our dataset with p-values less than 0.01 in a black box setting. Here, we present results for CIFAR100 on 6 different attack strategies, and the complete results can be found in the main paper. In summary, dataset inference as a defense requires few private points to prove ownership of an ML model. It can be performed in less than 30,000 queries to the adversary and does not require white box access to be successful. Most importantly, dataset inference can be useful for models which have already been deployed in the real world without making any changes to them, such as requirement of overfitting or retraining. Finally, it does not have a trade-off with task accuracy. Thank you for your time, and if you liked our work, you can find our